Good morning, everyone, and welcome to today's computer vision lecture. Last week, we looked into object recognition and concretely discussed the challenges of object recognition. We looked at different terms in recognition, like classification, localization, detection, and saw that these are increasingly more complex tasks. We saw why object recognition in general is tough in computer vision. We looked at different approaches, like very simple ones like template matching. They are simple and maybe not that powerful, but for a controlled environment, they may be very helpful because they run very efficiently. We saw histograms, and then we looked into machine learning, and we saw most machine learning methods. They don't work too well on the raw data, in particular, not in computer vision. So we need to pre-process the data by finding features, and we would feed them in to a machine learning model. But neural networks are different because they allow us to self-learn a hierarchy of increasingly more complex features. Then we discussed in detail convolutional neural networks. We started with the structure of a neural network, what neural networks are very helpful for, the history of neural networks, and we saw how we can do a feed-forward propagation using the sum of products and putting that into an activation function like sigmoid or ReLU. In order to find our parameters, we need to optimize a cost function, for example, a squared error term, or maybe for classification tasks, we can use the cross entropy. And we saw that we need to do gradient descent in order to optimize these parameters by finding a minimum in the cost function. We saw various variations of gradient descent. In order to calculate the partial derivatives, we need backpropagation so we can find them efficiently. And then we started looking into deep learning, neural networks that have lots of hidden layers, which comes with various challenges. And then we saw convolutional neural networks, which allow us to work on the 2D structure that we put in, which is an image. And obviously, this can be extended to 3D, whatever, or these convolutions can be applied to problems different to vision. We saw the motivation of convolutional neural networks, some of their key properties, and how they work. And we saw that most of a big or deep neural network in vision is actually the feature detector, and the actual tasks that we are learning are just the last few fully connected layers. We saw some more challenges in how to calculate the partial derivatives, compared various approaches, and looked into deep learning frameworks that do a lot of that work for us under the hood, and we can use them high level in Python to build sophisticated architectures. Model selection, so optimizing the hyperparameters is challenging, but there are various approaches to that, as well as there is AutoML that we looked at. We also saw why GPUs are so helpful to train convolutional neural networks or neural networks in general. But we also see we need CPUs, so we contrasted the differences. And we also looked at a couple of selected architectures that have become popular up to the latest version of YOLO 12. So that was the deep learning part, and a lot of vision projects in this course use deep learning, but you can also use other approaches depending on your project. I'll say more about the project next week, because we will most likely finish the content of these lectures next week. Our goal today is to look into image sequence processing, and next week we are hopefully able to finish the outlook as well as the foundations of mobile robotics, in case you have picked a mobile robot, if you want to do a robot vision project. And then at the end, next week, I'll say more about the projects, but we should first continue with the content. So today, we will not look at just static images. We'll look at image sequences. We will motivate that. We'll see also how we can track image sequences. And then there are lots of problems or lots of methods in order to work on image sequences. You can use a neural network approach, like a recurrent neural network, that can work on temporal data, and you can customize it to work on vision data. But this is something that you would rather see in your deep learning class. And in this course, we will use some other approaches. We will look at the end into the optical flow, which is a more lightweight approach, yet works reasonable. And we will look a lot today into temporal models and Kalman filters. These approaches are also much more low weight than training a huge neural network. And the beauty is that these filters, a Kalman filter, can be applied to lots of um, sequence problems and not just to vision. We can customize it to work on vision, but overall, I think that Kalman filter is a very helpful tool that you can use for lots of other problems. And and then you'll have your deep learning class where you may see some recurrent convolutional neural networks. And eventually, based on your tasks in the future as a data scientist, you'll be able to pick the right methods because deep learning is not a silver bullet and will not always lead to the outcome you expect. So you should also know some other methods. And we'll be looking into largely the Kalman filter today, but in order to understand it, we'll need to do first some readings and discussions of temporal models as a foundation. So in computer vision, we not just have static images, but we have image sequence problems. And there is also motion in computer vision. And dealing with motion is a subfield in computer vision because we want to estimate, we want to make estimations and analysis related to motion in image sequences. So we have like a video that would be an image sequence. And motion, therefore, adds another dimension in computer vision, which is time. And motion in computer vision is something you see in actually many cases, and we have lots of examples where we deal with motion in computer vision. Maybe we want to track features within a scene. So we have an image sequence. There are certain features like corners of a car or just corners of some object that is moving, and we want to track these features. And based on tracking the features, we can maybe track the whole object. A recurrent neural network would maybe combine these two tasks into one model, but first of all, it's two different tasks. We could also segment objects based on motion. Maybe you want to do motion stabilization, a camera, so you move your camera, yet the image or the image sequence gets stabilized, so it's not shaking, even though your hand was shaking. Maybe you want to recognize a scene. Maybe you want to reconstruct surface of some object when you have a 3D reconstruction. Maybe you want to understand behavior, scene dynamics. Something else could be collision detection and avoidance in an autonomous car. So there are actually lots of examples where we deal with motion in computer vision. And one thing we could be dealing with is tracking an object. So we would start with an initial image and recognize various objects in there. And then we have more images in that sequence where new objects or say objects in general are appearing. And we may want to track one object throughout that scene, or we want to track multiple objects throughout the scene. So somehow we also need to create IDs for our objects. So we are able to actually link one object in the first image with the objects in the next image. So we would be able to actually track it and not just independently find new objects in each image sequence, but rather we want to track that object. So that could be a challenge. And there's one example here of tracking. This is some photos from London, an image sequence, and in front of us is a bus, and we may want to track that bus, but we could also maybe try to track these lamps up here, this illumination. things like this. Or we may wish to track image sequences in, for example, some surveillance system like here. This is maybe from the police to track cars in here for various reasons. And we see cars are moving within the image sequence, and we need to assign an ID initially, for example, to this car, and we want to be able to track it later throughout that scene. Or this car here got tracked, and what we see here is its trajectory. And somehow we need to build these systems, and for this we will discuss the right methodology today that we can use. And I want to discuss a lot today the Kalman filter, which is a very powerful model used in signal processing. We can customize it to vision, but we can use it for lots of other problems like tracking objects, using other sensors like distance sensors and an autonomous robot. So it's overall a very powerful model. And all you will see is that the Kalman filter does not really care what the input is exactly, but we're able to track something in the input. And the input, if you customize it to computer vision, would probably not be the raw image, but potentially features. And you would try to track or you would try to process these features in a Kalman filter. So later, the stuff we will see will not have images as inputs, but rather we will see some generic input, which could be features derived from images. And in order to motivate the idea of the Kalman filter, which is one of many temporal models, we will look now at a couple of problems. Imagine you are standing in the jungle and you are watching a small bird flying through that jungle. And from time to time, you will see that bird, but sometimes the bird is moving and you may not see the bird all the time because maybe the bird is hidden behind a tree or a big leaf when flying. But you will be able sort of to guess where that bird is right now, even if you don't see it or you only partially see it, but you saw it moving before and you saw its trajectory. So you can sort of guess where it will appear next so that you see it again once it's, I don't know, past a tree or something like this. So humans can do this very well. And there's another problem. Imagine you were a radar operator in, for example, World War II, and what you see is you don't see the objects on the radar every time, but rather you would maybe have some blip popping up every 10 seconds on the screen. Yet now maybe 5 seconds have passed and the radar doesn't fully show you where that object is right now, but you have seen it before on the radar every 10 seconds. And so you're sort of guessing where it may be next. And then at some point it will pop up and it's maybe exactly where you estimated or maybe not exactly there. And from then on, you'll have a new trajectory and you'll be able to estimate it again in the next few seconds when you don't see it. Or you could have a related problem. Imagine to the early days when Kepler tried to reconstruct the motion of planets and come up with his laws of planetary motion. He somehow must derive them. And actually, he also started with collecting observations of the planets through his equipment. And from then, in these measurements, they were also quite inaccurate. And he tried to estimate how the planets are moving and then measured again. But overall, he had a lot of noise in his measurements. But then he was able to predict how the planets move. And from that, he derived his laws of planetary motion. So here we see all these problems are related because we observe something, but what we observed may have a lot of noise, and we try to estimate a subsequent state. And what all of these three tasks, so the bird, the radar, the planet motions, have in common is the following. We want to estimate state variables, for example, position and velocity, but we only have noisy observations over time and not all the time. And the task we are doing is called filtering. Sometimes filtering is also just called state estimation, but we'll talk in a moment about why this is actually called a filter and not a state estimator. Yet it's actually two synonyms. And when I taught this course for the first time 5 years ago, I didn't discuss the Kalman filter because I was too busy creating that course. And then I said, I want to discuss it in the second year and add it to the course. Yet the Kalman filter overall is quite a tough topic. I don't know, did any of you ever study the Kalman filter before, or maybe you've seen it somewhere before? If so, maybe thumbs up or green sticker. If you have never come across this, just the opposite. You'll find it in, well, one person has seen it. Maybe you want to tell us where you have come across the Kalman filter and for what kind of problems. Either you can turn on your mic or you can send it in the chat as you wish. And while we're waiting for your answer, I'll just go ahead and then refer back to your answer if it comes through the chat. So when I created this part of the course then a few years ago, I wondered where could I find a very good explanation of the Kalman filter that wouldn't require like reading hundreds of pages. And my favorite AI book is Russell Norvig, so AI, a Modern Approach. And there's a very good chapter in it, which is called Probabilistic Reasoning Over Time. It's quite a big chapter with lots of different models. And it also includes the Kalman filter. And the Kalman filter is in the Russell Norvig book, just a couple of pages, maybe, I don't know, 5 to 10 pages or something like this. But it turns out if you try to read just these 5 to 10 pages from the probabilistic reasoning over time book, you won't get much out of it because what the book requires is some background in so-called temporal models. So we first need to study temporal models today, and then later today we will start looking into the Kalman filter as one specific temporal model that makes certain assumptions. So we will start now with temporal models, and we look at different tasks that temporal models can do. We'll look at some of the constraints they have, and once we've discussed the temporal models, which are very generic, we will make some more constraints and then have our Kalman filter, which we can use for vision problems, but also for totally different state estimation problems, like you have seen before with these examples. So you can feed in the signal, which can be raw data, maybe for some problems, or it can be features for other problems, like in vision. And the Kalman filter, by the way, is something that was devised in at the time when the US planned to send astronauts to the moon. This was a huge project and led to major investments in the US because lots of technology and methodology was needed in order to fly to the moon. And this is also the time when the Kalman filter made progress. And the Kalman filter was actually used to fly to the moon. But in order to understand it, we need some more background theory, like for temporal models. So in temporal models, we will always deal with a series of snapshots over time. We will call them from now on time slices. So we are working with discrete states, or the states may be continuous, but we will deal with with discrete time steps. So time step 1, time step 2, time step 3, and so forth. The variables, they may be continuous. And each time slice contains a set of variables. Some of these variables are observable, while some are not. And we're working, as I said, with discrete time steps. You can deal with uncertainty over continuous time if you wish, but that would be a totally different theory. What you would need is you would need to deal with stochastic differential equations, or SDEs, and this can be used um, to study continuous time, but in computer science, we anyway deal often with discrete time steps. So we can simplify this and work with these temporal models that we're looking at today. We don't need the stochastic differential equations. But what is important is some variables are observable while others are not. And we will assume that the same subset of variables is observable in each time slice. So it's a simplification. So some variables are always observable and some are not. And the setting which are observable and which ones are not does not change throughout the experiment. That's at least what we will assume. And we will have capital X in bold at time step t. That denotes the set of state variables at time t, which we assume to be unobservable. So that's the ones we want to estimate. And then we have capital E in bold T. That denotes the set of evidence. This is the stuff that is observable. And the observation at time t is capital T is a capital E at time t is small et for some concrete set of values. So a small e is always the concrete set of values at time t. And we need a little bit of more notation soon, but we are starting now to motivate an example. And this is the one we are using throughout this chapter. So we will see what is actually observable and what is not. Now, our setting throughout today's lecture is, imagine you're a security guard and you're stationed at a secret underground installation. And you never get out of the underground installation, but you want to know whether it's raining today, which you cannot see, so it's unobservable to you whether it's raining or not. But your only access to the outside world occurs every morning when the director comes in. So the director lives outside the installation, and the director comes in but does not talk to you. And the director either comes with an umbrella or without an umbrella. So this is your evidence that you're observing. And at every day t, the set et contains only one single variance, single evidence variable, umbrella t or ut, which is a Boolean variable, whether the director brings an umbrella or not. And that's your observable part, and the unobservable one is your xt. That contains a single variable if there is rain at time t, or just in short, RT for short. And you want to estimate whether it rains, so you want to estimate RT from your evidence ET, as well as your past states. And for this, we need our temporal model that we will now motivate step by step. But we need a little bit of more notation for the time slices. And we will assume that our state sequence starts at t0. So this is where your state sequence is starting, but we assume that all the evidence starts to come in at t equals 1. So we're starting with t equals 0 for the state variables, and evidence comes in as of the next time slice. And we will also have a notation a:b, which denotes the sequence of integers from a to b, where both a and b are included. So if we have a notation like capital X with the index a to b denotes all the variables from x at time a to x at time b, and a and b are included. So as an example, if I have u from 1 to 3, that corresponds to the variables u1, u2, and u3. And U, remember, stands for the umbrella. So here we have seen this would be the evidence. So this notation A to B can be applied to both the evidence as well as the states that you want to estimate. And now we need a few more models, and then actually we have everything our temporal models need to do, and we later just need to glue these models together in order to build increasingly more complex things we can do with them. What we need is a transition model. So what is a transition model? We have our state and we have our evidence variables for a given problem. And we need to describe two things. We need to describe the transition model, how the world evolves, so how our state variables that we try to estimate, how they evolve over time. And later, we need also the sensor model, and the sensor model allows us to describe how new evidence gets plugged into the model. So the transition model is the first thing, and the transition model specifies the probability distribution over the latest state variables given the previous values. So it's important we're dealing with a probability distribution, so it's a capital P in bold. And I want to estimate, or what I want is, I want to know what is my current state given all the past states. So these are conditional probabilities that you have studied also in your introduction to statistics. And I also asked you last week to review some of the stuff because later we will need a Bayes rule, maybe in an hour or so, half an hour, we'll see. And who have you revised the Bayes rule? If you weren't comfortable with it anymore, maybe thumbs up if you're okay with the Bayes rule, or maybe different reaction if you're not comfortable with Bayes rule. We'll have a quick example later just to make sure we're all on the same page. But I only see positive reactions, which is great. So the transition model helps us to get our current states given all the past states. And what we get is the probability distribution. Now, this one here can be quite tough to calculate because T may be very large and I need to look into all the past states. That's something that is actually not very practical. And as T grows, say T gets bigger and bigger, then I need to use ever more past state values. And that means as T gets bigger, calculating this here gets slower and slower, which is not very good. So, and it could also be statistically very difficult to estimate this reliably. So what we need to do is we need to use the so-called Markov assumption. The Markov assumption specifies that our model P of x at time t, given the past states, only depends on a finite fixed number of previous states. Maybe the last one, the last two, or the last 100, but it's a finite fixed number of previous states that we incorporate. All of this is part of Markov processes, or sometimes also called Markov chains, that were studied in depth by the Russian statistician Andrei Markov, who worked on this more than 100 years ago. And we can, for example, have a first order Markov process or a first order Markov chain in which we assume that we simplify this here. So this was from before. We said P of xt given all the past x's from 0 to t minus 1. This will be simplified now. And we will say in a first order Markov process that P of xt only depends on the past x at time step t minus 1. So this would be a first order Markov process, just in order to simplify this. You can have so this will lead to a much simpler transition model, and it also leads to something that you can compute simply much faster. You could also have a second order Markov process. And for a second order Markov process, you would say that P of xt depends on x at time step t minus 2 and at time step t minus 1. So here in these indexes, I could also just write t minus 2 colon t minus 1, but I can also just write it out and I say, so you need to read this, that P of xt depends on the xt or x at t minus 2 and x at t minus 1. And you could also try to visualize these Markov chains. And for this, we use typically a notation as something like this. So this would be an first order Markov chain, because we see xt only depends at xt minus 1. Xt minus 1 depends on xt minus 2. And so xt plus 2 depends only on xt plus 1. The second order Markov process looks a little bit more complex. So I have my xt plus 2, which depends on the one hand on t plus 1, but also on x at time t, but not on more. So this is just a visualization. And this visualization of graphical models is something we'll be using later in this course. You may sometimes hear a term that is a graphical model. I just mentioned this. Graphical models are a larger class of statistical models, which include Markov processes, but also some other more sophisticated models, but they all fall in this umbrella term, graphical models. And what we see here is we can also just visualize them quite neat. This is here specifically for a Markov process, but there are more complex or different graphical models as well. But it has nothing to do with computer graphics. It's just a graph structure in which we define this temporal dependency of the data. So these are all models used for temporal data, and they are based on a graph structure. And that's why we call this a graphical model, but it's not, I don't know, not a computer graphics model, just to highlight the terms. We are also making another assumption, concretely, that we are dealing with a stationary process, because with the Markov assumption that we have just made, there's still a problem. There are infinitely many possible values of t. And how do these distributions change over time? Because we could wonder, how do these distributions or these rules within the distributions, how to get to xt from t minus 1? We need some rules to define this, but these rules never change. Obviously, the concrete values change over time, but not the rules of how to get from xt minus 1 to xt. And that is concretely a so-called stationary process, so that these underlying rules do not change as t progresses. Obviously, the concrete values do change, but not the rules. So don't confuse stationary with static. Stationary here means the rules don't change. If we assume the values don't change in this process, then we would have a static process where the state itself does not change. But that's what we don't want. We want to deal with stationary, but not static. So it's two totally different terms. I've told you before when we introduced the transition model that we also need a sensor model. And for the sensor model, what we need to do is we now need to be able to combine the evidence variables with the state variables. And later, you will see the base rule, which will be very important to our temporal models. What I want to calculate is I want to know what's the probability of an evidence given the past state values and all the past evidence. Calculating this conditional probability distribution is very difficult. Again, t is not bounded. So as t grows, I need to look into ever more past state values as well as ever more past evidence. So this one here is again not very practical because it's very slow as t progresses, and probably overall this could be very difficult to calculate, and the estimations could be overall quite poor. So what I will do is I will also make a sensor Markov assumption. And all I want is I want to know that what's the probability distribution of the evidence at time t given our state variables at time t. I don't care about all the past states as well as all the past evidence. So all I want to know is what is the probability of my current evidence given my current state values. You may wonder, you would actually want something like, it's probably a question you're asking yourself now, um, why don't we calculate P of the state given the evidence? So what's the probability distribution of my state given the evidence? That's exactly one of the tasks we want to do later when it comes to filtering, as well as some other tasks in temporal models. But we need to plug in something there. And this one here is in fact far easier to specify in a lot of settings, that we can say what's the probability distribution of the current evidence given the current state. And with the base rule, we'll be able later to calculate, we'll be able to estimate xt given et plus some other stuff, but you'll see these tasks later. And this one here is our sensor model. So before we said the sensor model is quite complex, but we have simplified it now by putting a Markov assumption on the sensor as well. And sometimes the sensor model is called the observation model. And we will have an example now that I will develop with you on the whiteboard step by step. And just to make sure we're all on the same page, how that graphical model works. I've talked a lot now about the transition model and as well as the sensor model, and we will look at our concrete example now in our rain and umbrella world. We'll have an example. I want to know whether it rains at time t in the future. I want to know the rain at t plus 1. I also have my past state at t minus 1. And I'm visualizing this graph. So somehow my RT depends on RT minus 1. Which of the models is that? If I want to know how does RT depend on RT minus 1? I've mentioned various model names before. Maybe you can tell me which model that would be now. I'm not looking at the evidence yet, only my states. If you remember these names of the models, tell us in the chat. So I want to know, how does RT depend on RT minus 1? No answers in the chat. If you feel you have a clue what the name of that model could be, maybe thumbs up and I'll wait for you. Or if you're overwhelmed by this, maybe thumbs down or red sticker. This is the transition model that I mentioned before. Because in the transition model, we want to know how does RT depend on RT minus 1. And I need a table. So what I want to calculate is P at P of RT, because RT is the state variable. The evidence will be the rain. We're looking later on this, given RT minus 1. And so I want to update my state or the distribution of RT given my past RT minus 1. So this is subject to RT minus 1. And RT minus 1 is either true or false. And now I somehow need to come up with these conditional probabilities, and the book has defined them as an example, and we're using them throughout this course. We can say the probability of RT given a positive RT minus 1 would be 0.7, because this is positive, so RT minus 1 would be positive. And so what is, I'll read it out again. I want to know what's the probability of RT being positive. So this would be true. So P of RT is true given my RT minus 1. And if RT minus 1 is true, positive, it's 0.7. And I say it's 0.3 if my RT minus 1 was false. Now I see something interesting. I see a 0.7 and a 0.3, and they add up to 1. Do they always need to add up to 1, or is this just by coincidence? If you think they always need to add up to 1, send a green reaction. If you think this is just a coincidence or doesn't need to be, send a red reaction. And I only get green reactions, and I have to tell you, this is only a coincidence because I have this conditioned on RT minus 1. So we can, so this does not need to add up to 1. And I'll show you why. I'll write it out down here again. I say it's P of RT, and I just write it out in greater detail. RT must be true given my RT minus 1. And what needs to add up is if I add this up with P of RT is false given RT minus 1. That needs to add up to 1 because I have a true in here and a false in here, and RT is a binary variable. It's not a multivariate value, only binary. That needs to add up to 1. But here I have the conditions on RT minus 1, and I'm always calculating that RT, so I'm just writing this out, that RT is seems like the screen share just stopped. We'll share it again. So what I'm saying is that R at time t is true. And so you have to read this as P of RT is true given RT minus 1. And the conditional values here are for the RT minus 1. So these two values here, they don't need to add up to 1 because these are on the conditions. What would need to add up if I want to calculate P of RT is true given some value in RT minus 1 and P of RT is false given the same value. This would need to add up to 1. Maybe just confirm that you see the difference. So, fine. Because this is something that confuses a lot of people, and that's why I tricked you and asked you if this actually looks right or if it's just by chance. So this was also just a quick revision. And what we now will include is the second model, the sensor model. And I have the umbrella at t minus 1, the umbrella at t, and the umbrella at t plus 1. Because before we said, and I will write this out down here now, we need the sensor model. And I want to calculate P of ut given RT. This was our sensor model. So I have the evidence and the variable. So ut would be the evidence, what we measure, and RT is the variable, the unobservable one we want to estimate. And we say P of ut given RT, and that's why we have the arrow in this direction that ut depends on RT and not the other way round. And I want to now calculate what's P of ut given RT. It's again, just as a reminder, we use this up here. We can say ut is true. And given the RT, and for RT, we have a true and a false entry. And the book would something like say this is 0.9. So the probability that we have an umbrella, given that there is rain, would be 0.9. And the probability that there is an umbrella that given there is no rain today would be 0.2. So here it's 0 and 9, 0.9 and 0.2. So this doesn't need to add up to 1 because it's on the conditional and not on the one we want to um, have conditioned on, or that we want to have the ut given the condition. So this would need not add up to 1, these two values. But again, P of ut is true given an RT, plus P of ut is false given the RT. That would need to add up to 1. So you could just update the one up here where you plug in the u and so ut and RT and the same over here. And then you have the ut is true, ut and false, and you always have the same condition, RT, the same value. That would need to add up to 1 then. So very important to understand these conditional probabilities. And again, how can we read them out? We can read this out as the probability of having an umbrella today, given that there is rain today, would be 0.9, and the probability of having an umbrella today, given that there is no rain today, is 0.2. And this is just one way how to read this out and understand these. And the directions of these arrows is very important because we've said that ut depends on RT and in this model, not the other way around. You can also see this written in a nicer way here in the slides, but I just wanted to develop these tables with you step by step to make sure we're all on the same page. I've mentioned a note on the arrows and their directions already. Something you need in a temporal model is you need to have a prior probability at time zero. So you need to start with some initial values for your values for the unobservable ones, the ones that you want to estimate. And so something you're starting with, P of x 0. You could, for example, say it's half-half, 0.5 and 0.5. If you have multi-values, you could just put the same value into each of the entries at x0, or use some other function that depends on you, but we will later just use the most simple one possible. And then in such temporal models, and it's not just temporal models, it's a lot of probabilistic models, you would often see something that is called the joint distribution over all variables, because for any t, we could wonder, what does P of x from 0 to t and all the evidence from 1 to t, because remember the evidence starts from 1 and goes up to t, and the state values go from 0 to t. Somehow we need to calculate this, and depending on the conditions you introduce in probabilistic model, you can then calculate the complete joint distribution. And remember what we said before. We said before that we have a transition model. So this would be the transition model here, where we have the P of xi given the last x, so at I minus 1. And we've also introduced our sensor model, which is P of I given xi. And now I need to go from 0 to t, and rather than writing this out now for super long t, we use this multiplication sign where I starts at 1 and goes up to t. And we've seen that always we have at each step our transition model as well as the sensor model. But we are starting at I equals 1, and we need to go up to t. So we need to start also with P of x0 as the prior that we multiply in here. So we start the product with this, and then we go in the product sign from I equals 1 to t. So at each step, we need our transition model as well as the sensor model. We will later work with examples and make all of this more hands-on. But first, we need to progress a little bit with the theory. Now we've built all the essential steps now or all the essential pieces we need, and this joint distribution over all the variables shows us actually quite well what we have built now. We have our initial values to start with, and we have our state model, or that's the initial state model at x0. We have the transition model and the sensor model. But I told you our goal today is actually to do filtering, because we want to estimate x at time t given all this past evidence, all the past states, and we've made some assumptions about this. So what does filtering actually mean? There are various tasks of what we can do in our temporal model. One of them is filtering, which is state estimation. And there are a couple of other tasks we can do. Prediction means looking into the future. Smoothing means smoothing our trajectory from the beginning to where we are right now by also including all the evidence. Later we'll briefly see smoothing. And there's also something called the most likely explanation. That means we are right now in a state, what would have been the most likely sequence of evidence to get from the start to where we are now. And I've told you before, we have used these probabilities here at these conditional probabilities 0.7, 0.3, or here. Initially, we have set them, and we've just taken the values from the Russell-Norvig book. But based on your temporal model, you may don't know some of these conditional probabilities well. So you could also try to learn them, which is another task. Our focus today will be filtering because we want a Kalman filter. So first, we will look now more into filtering in temporal models in general. We'll briefly look at some of these tasks, just very briefly. And once we have done all of this, we can start building our Kalman filter, which makes some assumptions, but is very helpful for a lot of problems in signal processing as well as in computer vision. So what is filtering about? I've told you before, we want to do state estimation. And actually, what we want to compute is, we want to know the probability distribution of xt given all the concrete evidence from 1 to t we had so far. Because we cannot observe our state xt directly, like we've seen this with raining or where the planets are exactly or where the bird is exactly, because we only have evidence, but we may not see the object exactly, or it may be hidden at the moment. So we want to estimate it. And that's why what we want to compute is a state estimation or a belief state, what we believe the state to be, given all the past evidence and our past state values and so forth. And so filtering helps us to keep track of the current state. And there can be lots of challenges, obviously, when calculating this, because we may have very noisy input and we may have noisy state estimates from before. And this noisy input, so the noisy evidence somehow needs to be reflected in here. And I've also told you before, this is often called filtering. We could also call it state estimation. The term filtering actually goes back to the roots of this problem in early work on signal processing, because the problem was always to filter out the noise in the signal, because we want to estimate its underlying properties, but we want to filter out the noise in order to estimate the state. And that's why it's called filtering, but it's just a synonym for state estimation. And in our umbrella example, we want to compute the probability of rain today, given all the observations that we have seen before, if the director brought in the umbrella in all the past dates. And we will now describe filtering in a very generic way. And this very generic way is very hard to compute. And that's why later the Kalman filter will make some constraints, and this problem will become much easier to calculate. Yet will have made some constraints, and there's not just a Kalman filter, there are lots of other filters in the literature. They may make different assumptions. So in general, a useful filtering algorithm needs to maintain the current state estimate, and we want to update it. And we want to take advantage of the Markov assumption. So we don't always want to go back to all the past evidence and include it, but rather somehow only plug in the additional evidence. So this is our goal. We want to know now in the next step, xt plus 1, given all the evidence from 1 to t plus 1. But actually, all we want to know is we have our past state estimate, xt, given the past evidence. And somehow we want to combine that one with the additional evidence. And this is recursive. So it's the same for xt and the evidence from 1 to t. This would be then our t minus 1, xt minus 1, and the evidence from 1 to t minus 1, and we want to plug in the new evidence at time t. So we need somehow a recursive estimation, because we want to take advantage of our Markov property and not always go back and include all the past evidence in order to recompute our current state estimate. So f would be some recursive function that allows us to do this. Can be a Markov chain looking back once or twice, or first order, second order, whatever. But this function f would be a recursive function doing our state estimation. And this one, we can say, is composed of two parts. We want to know the current state distribution, and that one is projected forward from t to t plus 1. If you remember, this is the transition model because we have our state distribution at t and want to project it forward to t plus 1. So p of t, or p of x at time t plus 1 given x at time t. And we also want to include this new evidence through our sensor model. So number one is the transition model. Number two is the sensor model. And with that, we come back to some of the foundations in conditional probabilities, concretely Bayes' rule. And while the ones present have said they have done some studies in order to revise the Bayes rule, I still want to quickly double check and make sure that all of us are on the same page when it comes to the Bayes rule. So we'll do a quick revision of the Bayes rule and apply it to one example because we'll need it later throughout this chapter for our temporal model. So revision. Bayes rule. We can say that P of x, so now independent from our temporal models, so x and e, whatever, we just use two variables now. Want to know P of x given z. How can we calculate this? In fact, we can calculate this as P of z given x times P of x. And in order to have proper probabilities, we need to normalize by P of z. An absolute foundation in conditional probabilities, and I've just noticed the screen share ended unexpectedly. I'm sorry about this also in the recordings if there are sometimes issues with the screen share, but I have no control over this. It's a live lecture, not a professionally recorded learning material. We can assign certain names to this. We can say P of x is the prior. So the prior probability. P just depends on the value of x. Then our P of z is the normalizer, which just guarantees that we get proper probabilities later. The normalizer will play a minor role today. Often we just work with unnormalized probabilities just to make the formula look a little bit simpler, but I'll show you this later. And what I want to calculate is P of x given z. So P of x given z is called the posterior. And in a lot of statistical problems, I don't know how to calculate this posterior directly. So I need to use the prior, the conditional probability, as well as the last element, which is the likelihood. So P of z given x is the likelihood. And Bayes rule can be used for lots of problems, can be used for predicting whether or estimating whether someone is sick, can be used for classifying emails into spam or no spam. So we could wonder, what's the probability of spam given the input in the email? You can use this for spelling correction. You can use this in lots of machine learning models and for a lot of statistical problems. So it's probably one of the most important rules you see in your AI studies. And last semester, you have definitely seen it in your statistics course. But I wanted to offer a quick revision of these terms because you may have forgotten, or some students may have not completed the statistics course yet, which you should have, however, but we also have exchange students and others. And we will apply this now to a small problem. So we'll have an example of Bayes' rule. We can say 0.8% of the population, so of people, have a disease D. So there's some disease D, and 0.8% of the people have it. I want to know now, I want to have a test, and I want to test people if they have the disease. And this here was in my slides when I taught a different course at a different university before I got my professorship, long before COVID. So it has nothing to do, or it's not inspired by COVID. It's just something that has been mentioned in the statistics literature for decades. And I want to know, so we have a test, a D test returns a correct, positive 98% of the time, and um, a correct negative 97% of the time. And now Sean goes to the doctor and Sean gets a positive test. So Sean's test is positive. Now the big question is, does Sean have disease D? Do you think John has disease D? Maybe thumbs up if you think John has the disease, most likely, or thumbs down if you don't think so. Because, well, the test returned positive, but we also have some other variables. Maybe tell us with thumbs up or thumbs down if you think that Sean has the disease. Thumbs up, yes. Thumbs down or red sticker means no, does not have the disease, or green sticker, thumb. So I get a I get only positive results. So all the students think, almost all the students think that Sean is sick and has the disease D because it returned positive, the test. But the test is not necessarily always correct because we have a correct positive 98% of the time and a correct negative 97% of the time. And what is also important, most people actually don't have the disease. So it's 0.8 as the prior. And using our framework from before, we will now actually turn our text into this, and we will see whether John has disease D or not. And most of you felt he actually has the disease. Let's see. Our probabilities from before can be, or our text from before can be now turned into probabilities. We can say the probability of the disease is 0.08. This is the 0.8% of the people have actually the disease. Now we said we have a correct positive and a correct negative. What does that mean? We said a correct positive of the test is 98%. And correct positive means I have a positive test result given the disease. So the probability of a positive result given the disease, that's the correct positive, is 98%. And we have a correct negative, which is 97%. The correct negative would mean the probability of a negative result given, so negation of D, given that the person does not have the disease. That's a correct negative. So this is just from the text. And our question today is, does John have the disease D? So I want to know what's the probability of the disease given a positive test. And this one can be calculated with our base rule, because up here we had just plugged in an X and a Z, whatever. But and by the way, the base rule somehow also needs to be derived, but this is actually fairly straightforward, but I'm not doing it in the computer vision course because it's something taught in the statistics course. Do you still remember from your statistics course how the base rule was derived? Maybe thumbs up or thumbs down, but I will not derive it here in this computer vision course because we just assume that you know the base rule. And if you don't know it, you can return to your statistics course. It's actually fairly easy to derive it if you know about conditional probabilities, but not relevant to this course. So rather than X's and Z's, we can just plug in these new names now into our base rule or these new variables. And so we can say the probability of D given a positive test is then the probability of a positive test given D times the prior of D divided by the normalizer. Now it turns out we don't know how to calculate this normalizer, but we'll see very soon. And for this, we also need to go back to your statistics course, but it's something, the normalizer is maybe the least important one because we can try to calculate the unnormalized probabilities first and then normalize. So everything up here in the numerator we've already got, but we don't know the normalizer. So we can start with what we have already. But before we continue with this, yeah, maybe let's think about the normalizer. No, storytelling isn't too great, but we need a normalizer eventually. So who remembers the law of total probability? Thumbs up or thumbs down if this is something that rings a bell, law of total probability, because with that, we can, so some people remember it, that's great. With this, we can calculate the normalizer. So the numerator is simple. We said we already got it. And now let's calculate the normalizer in the denominator. We can say P of plus can be calculated by P of plus and D plus P of plus and not D. So these are joint probabilities. But we still don't know how to calculate these joint probabilities. So we can break a joint probability into something, and I'm removing, first of all, what I had put here. I can have a joint probability and I can break it up as a conditional probability times the prior. So it was before P of X and D, and I can break this up as P of plus and D, and I can break this up as P of plus given D times P of D. And I can do the same for not D. I can put well, let's use proper colors here. P of plus given not D times P of not D. And now I've got almost everything. We can start plugging in the numbers from above. Let's start with P of D. P of D was 0.008. So 0.008. The conditional probability of a positive test given the disease was 0.98. And we multiply this. Now in the denominator, we can continue. We still need the same two parts as from above. So 0.98 times 0.008. And what now needs to be done is this one here. So plus, what's the probability of not having the disease? Who of you knows this? So we know having the disease is 0.008. Maybe you can tell us in the chat, what's the probability of not having the disease? Wait for your answers in the chat. So 1 minus d, which would be 0.992. So we can plug this in, 0.992. Now the only question is, what is P of plus or P of a positive test given not having the disease? Who knows this? I'll write it out. P of plus given not having the disease. What's that? If you know it, send it to the chat. If you feel you don't know it, maybe thumbs down. One person says 0.02. Maybe you want to tell us why you think it's this way. You can also turn on your mic and tell us.
Because the probability of getting a positive test with the disease is 0.98. So the probability of getting a positive test without the disease will be 1 minus probability of 0.98.
So
That's
you
okay.
mean it would need to add up this with this 1 to 1, right?
Yes.
And that's a good guess, but it's not the right one because it needs to add up with this 1 to 1 because I told you um, I need to have P of minus given not having the disease plus P of plus given not having the disease must be 1. So it's 0.03 because what needs to add up is the one given the other one, but it doesn't need to add up on the condition. That's exactly what I discussed before with these tables. So it needs to add up with this 1 to 1. Maybe just everyone send me a green sticker or thumbs up if that's clear. It's very important you pick that conditional probability, not the other one. So lots of positive reactions. So, and then I have my 0.03 here. If you use a calculator, this would lead to something like 0.2085, which is 20.85%. So the question was, John got a positive test. Does John have the disease? Well, the chance is like 21%. Why is that the case? Because our tests are not always correct. We have a correct negative, a correct positive quantified here, but we also have a very low prior. It's only 0.8% of the people have that disease. So this very small prior also went in here. And eventually, the probability is quite low. Are you surprised about this low probability? Maybe send some reaction if this is something that surprises you. Because before, most of you said you felt that Chan actually has the disease. One person is not surprised that I think that was the person who also said before he does not think Chan have the disease. So this will need a little bit of explanation. So um, still, if you go to the doctor and you get a positive test, take that seriously, and I'll tell you why. Because in reality, you may have some symptoms. You may be bleeding, you may be coughing, or whatever. So you have extra evidence. So we would need a somewhat more complex model to put in that evidence. And then the probability would go up quite a lot. Maybe like flu or COVID, more people have it at the specific time because maybe more people are sick than less than 1% of the population. So that also needs to be included. But if you don't have symptoms, and you have a positive test for a disease that is not very common, then your positive test result doesn't mean much. That's why you need to talk to your doctor. If there's more evidence, maybe you can do a second test that works differently. You've also seen this during COVID. There was this quick test, and then there was a PCR, as well as a chain of tests. And you probably had symptoms as well. But if you don't have symptoms, still with this model here, you wouldn't get much out of it. So maybe you need a second test or need a model that includes symptoms. You can also update this model to include multiple tests. But we see just having a positive test doesn't mean that much without symptoms or other evidence. Is this something that was shown in your statistics course as an example for the Bayes rule? One person says yes, maybe some more responses from the others would be good. So I think this is something that helps a lot to in getting more results. So this is something actually provides quite some insights and it's probably a good application. So why did I discuss this with you? Because we will need the Bayes rule now for our temporal models. It can also be used for temporal data, not just for static data. Just to remember from before, we had this Bayes rule, we've introduced it, and we said we want to do filtering because somehow we want to do this recursive estimations or to estimate x t plus 1 given all the evidence from 1 to t plus 1 and but we don't want to recompute this from scratch. Rather, we want to use the evidence at t plus 1 and the past estimate of xt given all the evidence up to there. For this, we will need the Bayes rule, and I'll show you how. What we want to do is the following. Our filtering is in fact a two-part process. So we want to know x at t plus 1 given all the evidence from 1 to t plus 1. Maybe we can split that up. So we can say I want to know what is the probability, and it's always a probability distribution because P is in capital and a bold. You want to know what's the probability of xt plus 1 given all the evidence up to t and the new evidence. So we're just splitting up the evidence. Now you can apply Bayes rule to a construct like this. And the book shows in greater detail how to apply Bayes rule to such a construct. But it turns out it's actually not very difficult. But what I get is something like this. And the book shows it in greater detail. I can say, using the Bayes rule, I get the probability of my current evidence given my current state estimate and all the past evidence times this one here. And this one is the probability distribution of xt plus 1 given all the past evidence. Now, I can use the sensor Markov assumption. Because what I don't want is this one here, the probability of ET plus 1 given my current state and all the evidence up to t. So by using a sensor Markov assumption, this one just disappears. But do you see I've applied the Bayes rule? Is something missing there? Do you feel something is missing by having used the Bayes rule? Because before we always said we have a posterior, a likelihood, and for that we need, or for the posterior, we need the likelihood, the prior. So what is missing? Do you see if something is missing? Because there's no fraction. So one person sees something. Can you tell us what you're seeing? Turn on your mic or send it in the chat what you think you're seeing that is missing. Well, one person sees something but didn't tell us yet. Well, the normalizer is missing because we said before we always, when we use Bayes rule, we also need the normalizer. But I told you also before already, we don't always want to write out the normalizer. So if this would be just the numerator in Bayes rule, but the denominator we have left out for simplification. And what you do in as a notation, if you have these unnormalized probabilities, you just put an alpha in front. And this is our convention that in statistical models, that when you put an alpha in front, it's unnormalized evidence. But normalization is just something technical that then can be done quite easy, but we don't want to write out the normalization, just to keep it simple. So we put an alpha here. And then we use the sensor Markov assumption, and eventually the E from 1 to t disappears. So I've also written out alpha is the normalizing constant, make sure the probabilities sum up to 1. And the xt plus 1, given all the past evidence, is actually a one-step prediction of the next state. And the first term updates the new evidence. And we can also see that P of ET plus 1, given the current state estimate, can be obtained directly from the sensor model. This can be written out in greater detail, because so far this is just the first step, and we may want to we need to know how we can calculate these individual pieces. For example, the distribution of xt plus 1 given all the past evidence. You can calculate this. The book shows in detail how this can be derived. I'll show you this later with an example. I think this will make it much easier to understand from an example. And if you wish to see the exact general filtering formula, go back to the book or to the slide. It doesn't matter too much for now, because later in the Kalman filter, all of this will become much simpler, because in the Kalman filter, we'll make some more constraints. There's also some text in here in case you want to go back to this filtering equation, but we'll work on an example very soon with our concrete temporal model or our graphical model for the umbrella and rain, and then this will probably become more easy for you to see how it works. So there's some more technical details in here, but it's just in case you want to see this for revision. We'll start or continue with the example now and try filtering, so state estimation. So what's the rain given, or rain at t, given our past state, and the current evidence. And that's what we want to calculate now. And for this, I will switch back to the iPad. We'll calculate this together step by step. And you'll see it's actually not that difficult because we have a simplified temporal model and we don't use this highly generic equation. What you need to remember from before is this one here, because we've seen our transition model. The transition model was here, and the sensor model we have here. And actually, all I want to calculate now is I want to know what's the probability distribution, so a bold P, of R2 given the evidence of an umbrella from 1 to 2. So I want to know at time step 2, does it rain given, or what's the probability of rain right now given the evidence from the first 2 days? I need to start with day 1, actually day 0, because at day 0 we said that the probability distribution of rain at 0 needs to be something. And I'll use a vector notation now. I say 0.5 and 0.5. So 0.5 and 0.5 means no rain and rain. So just equal because we have nothing to start with. In the slides, I have written this in a well-formatted way just to keep it simpler and or in the slides that I can put more in the space. I don't use the column vector. I use a row vector that is transposed, and a row vector transposed is a column vector. It's just the notation I'm using in the slides just to keep it a little bit shorter and I can put more. Now I'll say day 1. I say that U1 is true. So on the first day, the director brings the umbrella. And what I need now is a prediction from t equals 0 to t equals 1. So I want to know what's the probability distribution of rain on day 1, because what I had was rain on day 0. I have the evidence now. So I need to know what's the distribution of having rain on day 1. And from our model before, from these very general filtering equations, we can actually say, and that's why we're looking at an example, we are going through the concrete values of R0, and we sum together the probability distribution of rain on day 1 given the rain of day R0, given the rain on day 0 times the prior of R0. So the prior is something we started with, and here we actually have our transition model. And rather than calculating this sum element-wise, we just use our vector notation. We said, when you remember our transition model, which was up here, we said the probability of having rain today, given that there was rain yesterday, so t plus t minus 1 was positive, the probability is 0.7. And if there was no rain the day before, the probability is 0.3. That's exactly what we put in these vectors now, 0.7 and 0.3. So we use vectors for this piece here. And the first value of R0, so we have a sum over R0, and the first value of R0 is this one here, which is 0.5. Now we have the next value in R0, which is just the other one, which is still 0.5. But I need to look at this probability distribution again, which was just this table from before, but now R0 has the other value, and then I need to put in here 0.3 and 0.7. It's just a consequence of the table before. But it turns out I have a 0.5, a 0.5 here, the 0.7 here, 0.3, 0.3, 0.7. Eventually, this doesn't lead to anything. So my transition model has not brought any insights because all I'm doing is I had this uniform state and I'm transitioning into the next uniform state because I don't have any evidence yet. I told you we have evidence, which is this one here, but this one is not in yet because first I have done my transition model in order to calculate the probability distribution of having rain on day one. So what I need to plug in now is my evidence. This is the second part of the filtering formula. So I need to know what's the probability distribution of R1 that we had just calculated here, given there was an umbrella on day one. And for this, we've seen the filtering equations. We've simplified them a little bit now for this problem because we have a simpler graphical model here. I can calculate. I need the probability distribution of the evidence given the state the state I'm estimating, which is rain here, times the probability distribution of R1. And this was just this one here. So R1 is just this one. And because what you see is I have applied Bayes' rule here because I want to know what's the probability of having rain on day one given there's an umbrella on day one. I don't know how to calculate this, but I can just use Bayes' rule, and that's exactly what I have done here. But I don't have a normalizer. And we don't care about the normalization yet. So what I can put here is just my alpha to say I'm leaving out the normalizer. We'll normalize it later. So, and then I can just use my vector notation from before again in order to calculate this. So I need my alpha. Because with the vector notation, one thing I'm simplifying now, when I looked at the Bayes rule, I had these sums, or I needed to sum up and so forth. And here, I'm just using this vector notation with the transition probabilities from the sensor model, and the transition probabilities from the sensor model are this one here, because I said the probability of having an umbrella on my day, given that there is rain, and if rain is positive, it's 0.9, and if it's negative, it's 0.2. I can just use this as a vector. I write 0.9 and 0.2, and my vector, or the distribution of R1 was just 0.5 and 0.5. And using these vectors, I can just very efficiently calculate this, and I don't need to iterate, but I need one new sign here, is this sign. And this sign is an element-wise multiplication. So I'm just writing this element-wise multiplication. So I'm just multiplying these two and these two. And what I will get is alpha times, so 0.9 times 0.5 is 0.45, and 0.2 times 0.5 is 0.1. Now I have these unnormalized probabilities. Do you think you see how we could very easily normalize these probabilities? Because we need to make sure that the first entry and the second entry add up to 1. Do you see how we could normalize them and then have normalized probabilities? Maybe thumbs up or green sticker if you see it. If you don't see it, send something else. Okay. All we need to do is fairly easy because we've seen before normalization was very complex and we didn't want to write this out anymore. But what we have is the probability of having a positive value is 0.45 and the probability of having a negative value is 0.1. And I can just normalize them by summing, or let's start with the first one. I can divide this by the sum of the two entries. So I can say 0.5 divided by 0.5 plus 0.1. And I can do exactly the same for the next entry that I divided by its sum. And concretely, this will lead approximately to a distribution that is 0.818 and 0.182 approximately. So this would add up to 1. Um, and as I said, fairly easy to do. I can just divide the entry by the sum of all the elements. So we see it's fairly easy now to always put just the normalizing constant, and the normalization is just done at the very end rather than doing it here early on. We need a little bit more, and then we are almost done with filtering, and then we can move very quickly to our Kalman filter, which simplifies this, or which comes with some of its own constraints, and that those constraints are very helpful for a lot of vision problems. But we first need to advance with the theory a little bit more in our Kalman filter. Now, we said we want to get to R2, or the probability distribution of R2 given evidence at 1 and 2. So far, we have only processed one evidence. And now we are coming to day 2, because so far we were in day 1. And in day 2, we see that there is again an umbrella. And before we process the evidence, we had used our transition model, which was this one here at P of R1. But now we actually need to calculate something slightly more difficult because we need to use our transition model, but reflect the evidence we had got at day 1 already. Once we have done this, we can incorporate the evidence at day 2, and then we are done. So halfway through. I can calculate the probability distribution of R2 given there was my umbrella on day 1. And I'm just doing the same as before, because what I've done here was the sum. I'm going through the concrete values of R0. Here I had used the prior, but I just need to use now a slightly different model here because I don't just have this prior anymore, but I have my R1 given evidence at 1. And this one here just stays the same, but we're just moving from time step 1 to 2. So I can say this is the probability distribution of R2 given R1, and I'm going through concrete values of R1. So because it's concrete values, it's a lowercase r1 times the probability of R1 given U1. And it turns out I'm just using my vectors as before. The vector for the transition was 0.7 and 0.3. For my first concrete value in R1, I'm using this one, the 0.818 plus, because I'm using this one here, because it comes from here, which was this one, because it's R1 given the umbrella at 1. And then I'm just doing it for the other value in R1, which is the 0.1A2. And I'm using just the other transition probabilities as in the first step. And it turns out that this gives me something like a vector that is 0.627 and 0.323. What does this mean now? Remember, at this step here, at the end of day 1, we had incorporated the evidence of umbrella 1. And our estimates have become better because we have included the evidence. But before that, in day 1, at the beginning of day 1, we have done something like we have done at the beginning of day 2, that we have only applied the transition model. For day 1, this didn't change the probabilities at all because they were 0.5 and 0.5, so this didn't change. The estimates became better when we plugged in the evidence. And now we are just doing a transition from day 1 to day 2. We don't have any new evidence, but we are using the transition model. But we don't have new evidence. And in fact, our estimates now are less certain because you see, before they were 0.81 and 0.18, but just transitioning from one day to the other reduces our certainty. So we have now 0.62 and 0.3, and there's a minor mistake I've just noticed. The values in the slides are correct. This is a 7, just as a small note, because it's normalized probabilities. So we are now less certain by transitioning from one day to the next day. And this makes sense because we're now in a new day. And all we have is the information from yesterday, so we are less certain about today, but we can advance by plugging in new evidence. And we know in day 2, the director brings in the new umbrella, or brings an umbrella on day 2. So I have now new evidence, and I can just do what I've done at the end of day 1, I can do now at the end of day 2. So I can say I want a probability distribution of if there is rain on day 2 using the evidence from day 1 and day 2 where an umbrella was brought in. And I can use the equations from before. So it's normalized, or it's a normalizer. So I can say, as before, I want to know what's the probability of U2 given R2, just the same as before, because we had said probability of U1 given R1. So U2 given R2. And then we had used this prior, but we don't need this prior anymore because now we also have the evidence from the day before. And we can say the probability distribution of R2 given U1. I have all the values I can plug in just as before. The probability distribution here was 0.9 and 0.2. And we do the element-wise multiplication. And we have this one here, the R2 given U1, which was this one here. So it's 0.627 and 0.373. We do the element-wise multiplication. Just to highlight, this value came from here. Well, maybe in a different color. This value came from here. I can do this element-wise multiplication, and I will get something like 0.565 and 0.075. And I need to normalize it, and this will give me approximately 0.883 and 0.117. So I see I have become more certain again on day 2 because I have now plugged evidence in. And at the end of day 2, when I have now seen 2 times an umbrella was brought in, I'm 88% sure there is rain outside, and I'm at 11 or 12% there is no rain outside. So I'm now more certain than at the end of day 1 because the umbrella has been brought in again. And this is something you can continue on your own as a practice if you wish, that you do this for the next day that an umbrella was brought in. But you can also say on the next day, well, maybe an umbrella was not brought in on day 3. And then these estimates will change a lot. Feel free to try this out. You've seen all the tools we need, and it isn't that difficult, in fact, when you use a concrete example rather than using these highly generic equations here, because all we have done, we have applied this now to our concrete example. So we've done filtering, and we'll be doing more filtering in the Kalman filter very soon, but we'll briefly look at a few more tasks in temporal models that can appear. In temporal models, we also have the task of prediction. So filtering is state estimation at the current day, but prediction can be that we look ahead into the future. So we want to know at some day t plus k, so k, or not necessarily day, time step k, because the examples we've seen days, but obviously you could slice differently in hours or seconds or whatever, or the next sequence simply, or next element in a sequence, like the next image. So we can look ahead by some k, which must be greater than 0, and I want to estimate what's the probability distribution of x at time t plus k, given the evidence I have up to right now t. So I need to look ahead. I'm doing a prediction. And for our example, this could mean in the umbrellas, we could compute the probability of rain 3 days from now, given all the observations we have up to here, which is also interesting. So not the probability of rain today, but in 3 days from now, given all the observations to date. You can come up with some formulas for prediction. I'm not discussing this now. It's just, all I want to know, all I want you to know is with prediction, there is another task looking into the future. You can also derive these formulas. It's all shown in the Russell Norvig book, if you wish. There is another temporal task. It's smoothing. And smoothing means we want to have a better posterior distribution over a past state given all the evidence we have up to today. So I want to estimate P of x at time k given the evidence from 1 up to the current time slice t, but k is now less than t, so some past k. So I have got more evidence in the meantime up to t, but I want to know a better estimate for my past states, given the new additional evidence that I've got. This can be used, for example, if you want to track a moving object. We have done some state estimations, but then new observations start coming in, and this could help us to estimate or to smooth a better trajectory than filtering. Because with filtering, we always estimate the current state, the possible trajectory, say, of an object we don't see in a vision task. But then later we get in more evidence. And with that evidence, we can try to go back and estimate a better trajectory of the object we're trying to track. So in retrospect, could give us a better trajectory. So this is what smoothing would be used for. And with our umbrella example, smoothing could mean we could compute the probability that it actually rained last week, for example, on Wednesday, given all the observations we got from the umbrella carrier up to today. There are more formulas in the book in case you want to study them. So there are very generic algorithms for smoothing or also the next task, but we will skip them now because we want to focus on the Kalman filter. For Kalman filter, we see more formula, but the last two tasks I still want to briefly mention. The next task is, so we've had filtering, which is state estimation. We've done prediction to look into the future. We've done smoothing to look back into the past. And there's one more that is called a most likely explanation. And what I want to know is, given a sequence of observations, I want to know the sequence of states that is most likely to have generated these observations. So we want to compute something like, I want to argmax, so I want to find the states from 1 to t that maximize p of x1 to t given all the evidence. So I want to know, given all this evidence that I got up to here, what is the most likely sequence of states I would actually have had. And such algorithms are quite helpful, like in speech recognition, where you later get more evidence, but maybe the evidence you get right now can help us to better estimate something that was said maybe with a few words before, because I've got now more words, more sounds, and this would actually help me to better understand the sequence of words that the speaker spoke when I'm trying to reconstruct from that noisy channel. This all also includes all noise. For, oops, I'm deeply sorry about, just clicked wrong. Just clicked at the bottom somewhere by accident. So I need to go to the right slide again. And the most likely explanation for applied to our umbrella example would mean that if the umbrella appears on each of the first 3 days and is absent on the fourth, then the most likely explanation is that it rained on the first 3 days, but it did not rain on the 4th. There are again highly generic algorithms for the most likely explanation. For example, the Viterbi algorithm that can be applied to, in general, to temporal models. And then if you make constraints on your temporal models, you may have more specialized algorithms. And the last task is learning. I've mentioned learning very briefly before and said we have these conditional probabilities, but where do they come from? In our umbrella example, they were set, but we could also try to find them based on evidence and our states that we're trying to estimate. And this is something you can also learn. And what you would do is you would use the EM algorithm, so the expectation maximization algorithm. We've seen EM very briefly when we looked at clustering a few weeks ago, and we can do EM clustering, but I said EM is a very generic algorithm, and it could also be used for this learning task here. These are the tasks you have in temporal models. So filtering, prediction, smoothing, most likely explanation, and learning. From now on, we will focus on filtering because before we've seen these tasks that we have studied. We saw the bird's flight, the radar, and the planets. And in all of them, we have something in common. We are doing filtering. Concretely, we're estimating state variables, position and velocity from noisy observations over time. And we have these time steps, and our variables are continuous. So the time steps are discrete. This is something we've always assumed. But the variables are continuous and noisy. We could make another constraint, and we could say that our variables are not continuous, but the variables only have discrete values. If you wanted to do this, you would need to pick a different model, for example, a hidden Markov model. These models were very popular until a few years ago in speech recognition, as well as some other problems. For speech recognition nowadays, for a lot of tasks, deep neural networks are used, but for some specific problems, these hidden Markov models are still relevant, but they have lost some interest in recent years. And then the variables are discrete, so concrete words you want to find in speech, but our variables are continuous, which makes sense to a lot of problems in visions where we want to estimate, for example, locations and stuff like this when we track a car based on evidence. So we want to deal with variables that are continuous, and this is what the Kalman filter does for us. So welcome back from the break. And the Kalman filter is one filter that comes with some constraints, and it allows us to use a series of measurements over time, but those that contain noise and other inaccuracies, and it produces estimates of unknown variables that tend to be more accurate than those based on a single measurement alone, because we want to estimate the joint probability distribution over the variables for each time frame. And so the Kalman filter is very helpful to deal with noise, and our measurements, in fact, they are noisy. And so we will have noisy state estimates. And we'll discuss the Kalman filter now and see this as one concrete filter because these general formulas we had before, they're extremely generic and we need to make some assumptions now, and we'll develop these assumptions step by step and then see how the Kalman filter works and why it has become so popular. So our bird's flight from before could be specified by 6 continuous variables at each time point. We will have 3 for the position, which are xt, yt, and zt. So the exact position of the bird, and the bird flies in this 3D space. So we also need 3 for the velocity along x, y, and z. We put this dot on top for meaning the first order derivative. So the change along x is denoted by xt dot. It's a notation used largely by physicists. And that means the change in x, the change in y, and change in z. So this the velocity in x, y, and z. But we will need more helpful or more useful conditional densities to represent these transition and sensor models. And concretely, we will use so-called linear Gaussian distributions. And the linear Gaussian distributions are something we will use. We will not discuss their theory in detail. We'll simply apply them in the Kalman filter. So we want to know the next state, xt plus 1. And that one must be a linear function of the current state, xt, but we also include some Gaussian noise. And in fact, this condition about the Gaussian noise turns out to be quite reasonable in a lot of real-world problems. So for this, I'll switch again to my computer, to the iPad, with a whiteboard. Ranger should be coming soon. So Gaussian distribution, probably just a revision, but it's one probability distribution, sometimes also called the normal distribution. And the Gaussian distribution has two parameters, which is the mean mu and the standard deviation sigma. No, let's write a sigma. Well, doesn't. No. So these the standard deviation and therefore the variance. So the variance is sigma squared. And we can define this probability distribution as P of x, where we have a normalizer that will come soon, and we can say it's e to the power of x minus mu squared divided by 2 sigma squared. And x is ranging from minus infinite to plus infinite. And since it's a probability distribution, we want the integral under it to be 1, which does not work with this function. And I'll just write the minus a little bit nicer like this. And that's why I need to normalize it. And it turns out I can normalize this by sigma times the square root of 2 pi. It's something that was introduced in your statistics lecture at the very latest. And sometimes this Gaussian distribution is also referred to as n of mu sigma squared. We have the parameter, which is the mean, as well as the variance or standard deviation. And this one, there are some special cases. One special case is a special case. Or one special case is mu is 0 and sigma squared is 1. And this is sometimes called the standard normal distribution. Who of you feels comfortable with the Gaussian distribution? Thumbs up, thumbs down. All okay. Something you anyway need throughout machine learning a lot. So this is what I had just written down, and you can also plot it. So when mu is 0, we have the mean here, and this one would be for a very tight standard deviation. The red one would be mu is 0, and the standard deviation or variance, the variance is 0.2, and the variance here is 1 for the red one, but you can also spread it out more like the orange one. But you can also shift it. So here the mean would be -2. So these are some of the visualization of this probability, this density function for concrete values of the parameters. And it turns out you can also use this Gaussian distribution for multiple dimensions. Who of you has ever seen this? Maybe this is the more tricky one now. Send me a positive reaction if you have seen something like this for multiple dimensions, so more than one input, or if you have not seen it. So one person has seen it. Maybe you can tell us what you have used it for, either in the chat.
No, we were taught about it in the machine learning course.
The machine learning course talked about it. Good. Multivariate Gaussian distribution. And we'll need this actually now for the Kalman filter. And it's actually quite similar to the one here. So this was the one for one dimension. And we can actually change this a little bit, and then it becomes highly generic. So it's P of x. Now x is a vector with more than one dimension. And I still have my e to the power of something. And before it was a minus here, and we had these squares. And now it's e to the minus of 1/2. And we will use a few new symbols. We will have our input vector x, and we will subtract mu, but mu is now a vector. So mu is the mean vector, because I need a mean in every dimension. And I will have a sigma, also in bold, since it's a matrix. It's the covariance matrix. So which includes how each of these two variable, sorry, if not variables, if it stores how a variable changes with another variable. This is stored in the covariance matrix. And I have x minus the mean vector, and I transpose this. And I have later here, again, x minus mu. And in between, I put the covariance matrix and I invert it. So it's x minus mu vector transposed times the inverse of the covariance matrix times x minus mu. This is something that is derived in the literature, so we just use it. But again, it needs to be a probability distribution. So it's actually quite similar to before, because we had mu, which was a vector, which was a scalar. Now it's a vector, and here we had the variance. And what we have now is the covariance matrix, because it's more than one dimension, and how these individual variables change with each other. This is what the covariance matrix will do for us. And then I need to normalize it. And the normalizer was before something like sigma times the square root of 2 pi. Sometimes the sigma is also moved in here, but then it's a sigma squared, the variance. And this is exactly the same now here for the multivariate one. It's 2 pi, but to the power of n times the determinant of our covariance matrix. Matrix. It's well formatted in the slides. I didn't come up with this Gaussian distribution in multivariate. It's been derived a long time ago, but we see it's actually not too different to what we have done so far. And it's just a generalization, also well typed here with but just what we wrote down. And you can also visualize this. So this would be a 2D, so we would have two parameters. So it's a 3D plot shown in 2D, and this density would spread out like this. So it's more like an elliptic density, more or less. And we see there is a Gaussian distribution in the one dimension and in the other dimension. There's one way how such a probability density function can be plotted. This is something we will need now um, when we build our Kalman filter. We start with one dimension, and later we will generalize it to multiple dimensions. For our bird's flight, we will consider that so we've seen before that bird flight goes in 3 dimensions, X, Y, and Z, and we have a change along X, a change along Y, a change along Z. And we will only focus on the X coordinate for now, and we will ignore the other coordinates. So we just look along one of these variables or one of these coordinates, just to start with one dimension. And we will see, or we will say that the time interval between observations will be a delta. So this is the time interval, can be 1 second, can be 1 minute, 1 millisecond, whatever, between the observations. It's fixed. And we will then assume constant velocity for now, and at least in that interval, and the position update would be given then. So we have our position in time t, and now at one time step further, so at t plus delta, we would take our xt and add on top the product of the velocity times the delta, which is the amount of time for one time step. So this is how we would update the position from one time step to another. But I've told you before, this is one thing we're doing when we do our transition model, but we will also add Gaussian noise on top, because we need to account for wind variation, slowdown of the bird, whatever. We've said before, and we are doing, when we introduced the Kalman filter, we said we would be exactly doing that. We say the update xt plus 1 will be a linear function, and that's also one of the constraints of the Kalman filter. There must be a linear function of the current state, plus we add some Gaussian noise on top. And for this, we can use these linear Gaussian transition models. And what we can say is we want to know the probability of xt plus delta, where we use our concrete. So this is just the generic variable. This is the concrete value xt plus in the time a delta, given our concrete xt and given the change along x. What I want to have is this linear Gaussian transition model. And what I put in as the mean was my xt plus the update on it. That's what we just did before. We said we take the velocity in the time delta. That would be the mean. And we will use our sigma squared as the variance. And this n refers to a normal distribution. And we want to know that one for xt plus delta. And with that one, we can estimate the probability of um, our updated xt plus delta, because we include in our model the xt and the concrete change and plug it into this Gaussian linear model. Linear here, we sum this together and then put it in a Gaussian transition model. And we now need a concrete graphical model in order to describe these dependencies. And sometimes, when it comes to graphical models, you will also hear the term Bayesian network. So, because we use a Bayesian framework and we build this network of how these variables depend on each other. So, Bayesian nets are one example of a graphical model, but there are others. And in fact, the one we saw before, all of this were Bayesian networks as well. And what we assume is we have our xt plus 1 depends on xt as well as the change of xt. That's exactly what we had incorporated so far. And we will also have position measurements, z, which are the measurements. And we want to know later what's the probability of zt given xt. And in order to update our conditional, or in order to update our state estimate, we will need the Bayes rule again. But we start with, we have these conditions, xt plus 1 depends on xt and the change of xt, and zt depends on xt. So it's just a somewhat amended graphical model than before, because we now have introduced the change as well, something we had not done before when we looked at our highly generic models, because we just said there is an x and what's exactly in x, it's a vector. But now we say x here is a position and a change, and we plug that into our next xt plus 1 by using these Gaussian or linear Gaussian models. And in order to update this, there will be a little bit of maths now, and it will look very complex, but then we use a concrete example and see it's actually not that difficult. So a key property of the linear Gaussian family of distributions is we say it remains closed under the standard Bayesian networks operations. So closed means if we use these Bayesian operations, we still deal with proper probabilities that fit into the framework of linear Gaussian distributions. And what we need to define now is, and again, it looks highly generic, we'll apply it to a concrete example and see that it's not that difficult, in fact. What we want to know is the current distributions or the probability distribution of our state given all the past evidence. So the state at xt given all the past evidence. We say that one is Gaussian, and the transition model, that's exactly what we have just specified before by using by adding the change on top of x. That one is a linear Gaussian model. So xt plus 1 depends on xt. We've seen this with the linear Gaussian and the change. And then we can say that the one-step predicted distribution would be given by something like this. This looks more complex than it actually is, because rather than a sum, before we dealt with sums for when we introduced the temporal models, here we're dealing with an integral. But later, when we use an example, we will actually be able to do this fairly easy, as you will see. But we can say that the probability distribution of xt plus 1, given all the evidence from 1 to t, what we are applying is here the transition model, and we have our sensor model. And in fact, we multiply them as before, but now we're dealing with continuous values. The examples we had before, we had discrete values, as you remember, because we said there is an umbrella or there's no umbrella. But now we're dealing with continuous variables. So rather than summing this together, we use an integral for xt. So at the end, we also need to say that this integral, or it starts, or we go through the values in xt, which are continuous, and we go along xt. That's why we still need to add this dxt. But this turns out, and it can be proven, that this is also a Gaussian distribution. So our operations that we're using are closed under the standard Bayesian network operations. That's important. And as we have estimated P of xt plus 1, given all the evidence, we can continue with this. And we can also say that we have this prediction where we want to have the probability distribution of xt plus 1, given all the evidence. This one is also a Gaussian, and our sensor model is linear Gaussian. So after conditioning on the evidence, the updated distribution is also a Gaussian distribution. And what we are saying is, I want to know the probability distribution. So it's just the base rule on the stuff before. So it's just a slight change to our temporal model equations. And we want to say the probability distribution of xt plus 1, given the evidence from 1 up to t plus 1, is just we multiply the sensor model with the one we just saw before when we have the one-step predicted distribution. This is just this one here, and we need to normalize it. So we leave out the normalizer and we just put in an alpha. This is also a Gaussian distribution. And it turns out you can when I talked about these filtering equations, I said there's this forward operator, something we just left out in this highly more generic equations, which we then simplified and used this for our umbrella example. It turns out this Kalman filter is very much related to these very generic equations before. All we need is now continuous variables. But we will turn this now into a concrete example. And we'll see a few examples in the one-dimensional case. And then we need a multivariate Gaussian to put this into a high-dimensional example. I'll just skip a little bit of extra text. If you want to do some further readings, feel free to look into this. But we'll look at an example. And I want to know, and you see this is actually not too different to what we did before the whole time with our umbrella and rain, but we are now using continuous variables, and we're using just position x of our bird that our vision system is trying to track. We are not feeding in the pixel values, but maybe the position of some features we have found of this bird. And we want to track this the object by using this feature. And the feature could be, or we could be using features to find the position of the bird, but the bird is sometimes occluded, and we have from time to time updates that we feed in there. This is how you need to imagine it. So it's highly generic, can be linked to vision like with this bird, but could also be used for some totally different signal processing problem. But you're not feeding in the actual images, but rather something that you have pre-processed like features or some object detection that you're putting in there. So it's not that this will not be running very well on your raw pixels. You would be doing some pre-processing. Now, I want to know what's the prior probability distribution. We needed that before, and we said for our umbrella and rain, just 0, 5, 0, 5, half, half. But now we are working with continuous values, so we could just use a Gaussian distribution. And I don't care about the normalizer now. I just want to keep it simple, so I just write the alpha here. We've seen before the normalizer, but we just want to keep it short, so we put an alpha here, and we have our Gaussian distribution where we have our concrete value, or we're starting with x0, or x0 is the variable, and we have an initial mean and a sigma 0 squared. So this is the first variance that we are dealing with. How to set the variance and the mean, this is something we'll discuss later, but for now we just assume that we have these values. And we use the same alpha throughout this now. So it's not that alpha always has the same value, but we just use the same symbol and say, whenever we have done this one here, we just normalize and we continue working with normalized distributions. Now we can do our transition model and we're adding the Gaussian noise on top, but we also have the constant variance sigma x squared. And in fact, we had our xt plus 1. You've seen it before. And when we put this into the Gaussian or the linear Gaussian distribution, and we want to know now what's the probability distribution of xt plus 1 given xt. And again, we're just using a Gaussian distribution for this, and we say it's xt plus 1 minus xt, so the one we're conditioning on, and along x, I also have a variance. So this is sigma x squared, and if you use this now for y and z, it would be sigma y, sigma z, and so forth. And our sensor model also assumes Gaussian noise with variance sigma z squared. So the z here does not mean dimension z, but it means the measurement, because before we said we care about variable x that we estimate, and we could also do this for y and z, but the z here means the measurement, and it doesn't mean dimension z, because we're just working here on the one-dimensional case. And for this, we say the probability of the measurement given our state, we are also using a Gaussian noise. So here we set zt minus xt, the one we condition on, squared, and so forth. So it's overall not that difficult. I know it, first of all, looks a little bit difficult, but it isn't that much. And something I just want to notice or quickly add here, I say minus a half. And this minus a half is something that is actually the 2 here, the 2 sigma squared. So this has not disappeared, but rather than writing 2 sigma squared in from now on, we always move this 2 out. So it's minus a half this divided by sigma squared. Just as a quick note that we just moved the 2 out of this, but it's still the same, but it looks neater because we will be soon manipulating some of these terms, and then it's helpful if we have moved out this 2 and say minus a half this one. Now, we had introduced our prior, the distribution of x0. Then we want to do this one-step predicted distribution that comes from the first Kalman filter update that we had just introduced before. It was something like this one here. We had this integral because we wanted p of xt plus 1 given the evidence, and later we plugged it into p of x t plus 1 given the evidence up to there. And we plugged that in here. And essentially, that's what we are doing now, because I want to know p of x1. So I'm just transitioning from x0 to x1. I don't have any evidence yet, but I can say, well, this is p of x1 given x0 times p of x0. And x0 is continuous from minus infinite to plus infinite. So all of this is not very different to what we did before with our umbrella and rain example. There it was just discrete. We used a sum. Now we're using an integral because x0 is continuous. And on the last slide, we said this is a Gaussian and this is a Gaussian, so we can reflect the noise in it. So these e's, or these exponential functions, are just the ones we defined on the last few slides before, because we said this is the initial distribution of x0, this is the transition probability distribution, and we just plug in them in here. And then all we are doing is we want to merge these two exponentials, because it's e of to the power minus a half this times e to the power of minus a half this. And we can just merge this together into one exponential. So what we are doing is we are just multiplying this and this. So we're just multiplying two fractions, which is fairly easy. And it's then this one, because in this, you see in the denominator, it's sigma x squared and sigma 0 squared. And here it's just the rest of, so we put this up here and multiply it with this, and the sigma x squared with this one, which is there. So overall, not that difficult. It's just fractions. So it looks rather complicated, but in fact, it is quite easy. It's just fractions and integrals. And very importantly, you need to normalize this, which we have left out, but normalization does not matter yet. We want to simplify this one a little bit, or we want to rewrite it in a way. And it turns out there is a trick that is called completing the square. And completing the square is something you have most likely seen in your maths classes, in Math 1 or Math 2 maybe. Who remembers completing the square? Some do, some don't. So I'll just say a few sentences about it, because we'll just apply completing the square. If I have a quadratic, something like a times x0 squared plus b times x0 plus c, as the sum of a squared term, a times x0 minus b divided by 2a squared. And so we can express this, the quadratic, as the sum of this term and a residual or error, which is c minus b squared divided by 4a. Then this residual is independent of x0. So we can just express this quadratic as something like this and the residual term. Then the residual term can be taken outside the integral. So we are applying our completing the square to this stuff, but we say it's independent of the one variable x0. And that means if it's independent of x0, we can move it outside the integral. And this is exactly what would be suggested here. If I have my exponential and I had this quadratic, and the quadratic one will just be rewritten using completing the square, then I would have this first term that is still subject to x0, but the residual is not subject to x0. And then I can move it outside the integral, and the integral actually becomes much easier. And what gets moved outside that is independent of x0 is now less relevant, because we have the normalization, and it turns out that the integral over the integral of a Gaussian over its full range is now relevant. And so this one here, we will just ignore, because we don't really need this anymore. It's just some constant, and constants are something we want to keep out, and that's why we put the alpha there. And it turns out if you move this out and you apply the completing the square to what we had done here, then this becomes much simpler. And eventually we will see the probability of x1 will be then just an exponential, where x1 gets, where we subtract the mean from x1, and we will have the sigma 0 squared plus sigma x squared. So we notice that the residual term can be moved out, and this looks now far simpler than before, because before We had something like this. And actually, most of that here was not that necessary because we could apply completing the square. And this is something we will come back to in a few minutes and see that this actually helps us to notice something super interesting in the Kalman filter, but we will be there very soon. The one-step predicted distribution is a Gaussian with the same mean mu0, and the variance is equal to the sum of the original sigma 0 squared and the transition variance sigma x squared. This is exactly what we see here. So our mu0 is the mean, and the variance is sigma 0 squared plus sigma x squared. So it leads to a massive improvement, massive simplification when we use this Kalman filter. But we need to complete the update step. We need to plug in the evidence now. So we need P of x1 given the evidence Z1. And these are just the equations or the formula we saw before, that we have our sensor model Z1 given x1 times the prior of x1. Again, these are the exponentials. The P of x1 is just the one we saw on the last slide, where we use the completing the square. And our sensor model is something we defined as well before. So we can again try to merge these two exponentials. So we have this fraction and multiply it with this fraction. Something I'm not showing now on the whiteboard because it will take forever to write, but feel free to do these as well if you wish. But eventually, this looks more complex than it actually is. Actually, what we have done is we have these two exponentials, just move them together in one exponential and apply completing the square. And what you will get is, you want to see that P of x1 given z1 is a Gaussian distribution, which we need to normalize. But we have our x1, and all we need to subtract from x1, so the mean is this one here. And the mean is sigma 0 squared plus sigma x squared times z1. I'm not reading this now fully out, but we see all we need for the mean is a z1, the mu0, and all these variances. And the variance here as well is sigma 0, sigma x, sigma z. We add them and multiply them and divide them by the sum. So completing the square here is super helpful because we can express our mean, the one we are subtracting, and the variance simply as terms of the existing sigmas and z1 and the previous mu. So we have done now one update cycle, and we still have Gaussian distributions. The first part of the update cycle was this one. It was here, the transition model, and then we used the sensor model and the outcome of the transition model. And each of these updates is now super interesting because we can express the mu and the sigma of values we already know. And this is just summarized here. So my new mu and my new sigma squared, so the variance, can be expressed from the old mean and the variance fairly easily. It looks more complex than it is, but something like this can be calculated super easily, and something that makes the Kalman filter quite interesting. And these previous equations we saw, in fact, they play the same role as the general filtering equation. All we did this time was we assume that we use Gaussian distributions because we deal with continuous values. And I've shown you how we can calculate this new mean and the new variance. And in fact, these are just some weighted ones from the existing ones. This is explained here a little bit more in the text why this is interesting, but this looks more complex than it is. And what you should remember is by using these Gaussians, we can fairly easily calculate the new mean and variance from the old mean and the variance, as well as the measurement Z1. There's a little bit more text for your revision if you wish. And we have one example of the Kalman filter. So just what we have done with concrete values. We see that we start with P of x1. And for this, we have this green Gaussian here. We have the mean, which is here. So our initial mean is 0, and our standard deviation is 1.5. So the function spreads out a bit. Then we have our transition noise. So to get to x, oh, and sorry, I made a mistake. Just forget the last 30 seconds. We're starting with P of x0, which is this red-orange one. This is the one that has mean 0 and sigma 1.5. So it's the orange one. And we have our transition noise, and it's something we also saw with the umbrella and rain. When we do the transition from one state to the next state, we don't have new evidence at that moment, so our estimate becomes less certain because we are now in the next day and we didn't know if it rained, but we're waiting for more evidence. So just transitioning from one time step to the next step reduces certainty. That's why P of x1 we see is more spread out. So the transition noise was sigma x was 2, and we also have a sensor noise, which is less, so it's sigma z is 1. And we see that just transitioning from P of x0 to P of x1, we lose certainty because this Gaussian is more spread out. But then we have now a concrete measurement for the position, which is Z1 is 0 to 0, 2.5. So Z1 is 2.5. And with that, we get a much better estimate. So we have a much smaller variance and we are much more certain. The mean is not exactly, not necessarily 2.5, because you've seen with the equations before how we can calculate the mean and the variance, but we plugged in our evidence, which is noisy, but we get a much better estimate now of our distribution of x1 given the measurement. So you see, we are starting with an initial state. We are then transitioning in the next state. We are losing certainty. And when we plug in evidence, we become more certain. And this is now one round of transition and plugging in the sensor noise, and we become increasingly more certain. And it's also something we saw with this general model before. When we thought about umbrellas and rain, we saw from one day to the next one, we lose certainty, but when we plug in evidence, we become more certain again. And it's fairly easy to calculate these new means and variances just by using these equations here. This is the beauty of the Kalman filter, and that's why running these calculations in the Kalman filter are highly efficient, because I can fairly easily calculate the new means and the variances. The Kalman filter we've seen was for one dimension. We can extend it to more dimensions. And for this, we need the multivariate Gaussian n, and we have our parameters mu, the mean vector, and sigma, the covariance matrix. We've seen it before, what the multivariate Gaussian looks like, and it turns out you can extend this Kalman filter to a general case, where now x is a vector because it's not just one variable, but multiple variables. And we can also use this linear Gaussian noise as before, but we just extend it, because before we used the Gaussian function, now we use the multivariate Gaussian function to do this. And we introduce a few new symbols, concretely two matrices, F and sigma x, these matrices describe the linear transition model and the transition noise covariance. And we also have an X and sigma Z. Sigma Z is for, so H and sigma Z is just the same, the linear transition model and the linear transition noise for F and sigma X, and this would be applied now to the sensor model. Something we also did before in the one-dimensional case. Because when you apply the Kalman filter, you somehow need to start, and depending on your setting, maybe how good your sensors are, what environment you're in, you need to make some initial estimates and you need to calibrate the Kalman filter when you define the transitions, when you define the variance. That's something you need to do, and that's why when you use the Kalman filter, you need to optimize these parameters, like how certain are your sensors or how uncertain are they. That was described by the sigma, a small sigma for one variable, and now we have these covariance matrices to do this in a higher dimension. These updates, as before, for mu and sigma, this can be done as well in the general case. I will not read out or expect you to remember these update equations, but these update equations that we had before in the one-dimensional case, like mu and sigma, which were so neat to write, this can be generalized again to the multivariate example, and this can be written out. When you want to use the Kalman filter in your projects, and every year some students use this to track objects, for example, in some setting, maybe for a high-speed setting, we're running a deep neural network, could be very slow. Maybe they want to use a Kalman filter. I see this every year in some of the projects. You don't need to implement this from scratch. Obviously, you can implement your own Kalman filter, but then for the linear algebra part, use libraries like NumPy, but you can also use an existing library for the Kalman filter if you wish. There's a little bit more text in case you want to understand this general case, but for your projects, you would probably just use a library that implements this. The Kalman approach can be used for filtering. You can also use the Kalman approach. So Kalman approach here means this linear Gaussian approach, and you have continuous variables. You can not only use this for filtering, you can also use this for smoothing. So what we see in this example here is we have our bird's flight in X, Y. So it's not a bird flight, it's an example that you find in the book where we have in the XY plane, yeah, it's in 2D, it's a problem where we want to estimate locations and we have measurements and uncertain measurements. And for X and Y, so you have X here and Y there, we have this trajectory. So we have the red dots, which are the observed measurements. But based on our Kalman filtering, we are doing the filtering, which are, I'm gonna just zoom in a little bit. So the Kalman filter are these green crosses. So this is the filtered one, but we don't know the exact true locations because these are not visible. So we need to estimate them. The true ones are these blue boxes. So we make observations, but knowing that observations are noisy, we make these Kalman estimates, so the filtered ones, which are the green ones here, and we see there is some trajectory. We don't know the true trajectory of this object, but we have observations which are noisy, and we're estimating how this may go, which is the green trajectory. And this is filtering, but when we introduced the various operations we can do in a temporal model, we've also seen that we can do smoothing. So smoothing is a step looking into the past, taking all the measurements or the observations, also the ones up to here, and we go back in time and we try to get a better past trajectory. And by doing Kalman smoothing, we would see that this green one here becomes smoother and probably a little bit better than than when we filtered, because now we go back in time and use all the observations we have up to here, and we try with smoothing to update this past trajectory, and we see it actually becomes then quite close to the true trajectory, which is the blue one here over time. This is a figure from the Russell and Norvig book, and it turns out the Kalman filter, even though it was described or proposed for flying to the moon, it's a system still used today in numerous applications. And in computer vision, yes, you will not feed the raw image feed or video feed into the Kalman filter. You will pre-process to maybe detect some objects or have features, and this would be fed into the Kalman filter. So a more or lower dimensional signal would be fed in, like an X, Y, Z location, something like this. And the Kalman filter, as a summary, is characterized by continuous state variables and noisy measurements. And such systems are used for far more than vision. It is used for pulp mills, chemical plants, nuclear reactors, also estimating economies, plant ecosystems, flying to the moon, and it's used in many computer vision systems because you can execute this Kalman filter very, very quickly, and maybe with less resources that you would need if you run a deep neural network, a recurrent convolutional neural network, or something like this, which may need lots of training data. This system here needs far less data. So the Kalman filter, even though like 60 years at least old, is something super helpful. And I see students using it every year in some of their projects. Obviously, we've made some strong assumptions like this linear Gaussian transition approach. These are strong assumptions. And over the last 60 years, more extensions have been proposed, like an extended Kalman filter that does not use this linear assumption. It does a non-linear approach. Such a system can be helpful for certain other problems. Maybe it's more computationally heavy, cannot be described that neatly like the linear one, but it depends on your problem if you use this linear approach or the extended approach. If you want to track multiple objects, the regular Kalman filter will not work. For this, you need also extensions, and there's sometimes like for example, a switching Kalman filter. Say you have this object, you have one object, and you want to and this bird is flying towards this tree, and the bird is flying either to the left or to the right. This is something that the regular Kalman filter would not be able to handle very well. So with a switching Kalman filter, you would look at the one case, the bird is flying here and there, and you would split it, and later you could merge this based on new evidence. But there are probably hundreds, if not thousands, of extensions of the Kalman filter that have been proposed. If you need a more specialized Kalman filter for your projects, feel free to use one of them. And there are also some interesting videos on YouTube for the Kalman filter in case you want to study it in greater detail. Few last slides for today. In computer vision, there is a problem that we have actually already dealt a few times with, but we didn't generalize it and did not attribute a name to it. It's the correspondence problem. And the correspondence problem refers to the issue where ascertaining which parts of an image correspond to which parts of another image is tricky, especially where there are differences due to movements of a camera, time has passed, or movement within the objects in the photos. And this correspondence problem is something we try to address in lots of computer vision applications when we deal with image sequences. One is the optical flow, which will be the end of the chapter. We could also do stereo vision, so we would have actually two images from a stereo camera pair. So stereo means two cameras looking from different locations and angles at a scene. So this can help us to address the correspondence problem. And there are lots of other approaches like cross-scene correspondence or structure from motion or something like SLAM. And SLAM is something which is the simultaneous localization and mapping, something used in autonomous robots that we will discuss in the next chapter. This chapter will focus for the remainder on the optical flow, which helps us to find correspondence in two images that are subsequent in time. But we will do the optical flow in next week's lecture, which is just a few minutes, but we won't finish it today in the remaining 7 minutes. And I know today was tough. It was a tough day with lots of maths for introducing temporal models, formalizing them, and then we've applied this to a few problems, and then we've seen what kind of constraints or assumption the Kalman filter makes. And we've seen why the Kalman filter is so helpful. So in case you want to do a more ambitious project dealing with image sequences, not just with single images, maybe the Kalman filter could be helpful for some of your problems. Are there any questions towards the end? If you're all okay, send me a thumbs up. If you have a question, send a different reaction, and I'll wait for your question. So only positive ones. I know this was tough and you need some time for the revision. And when you use the Kalman filter for your problems in the projects, you don't need to implement it from scratch, but you've seen now a tool that is highly generic and helpful, and probably something that could be helpful for some of your problems as well. So I wish you a great Easter vacation and see you next week when we finish the optical flow and continue with mobile robotics and some selected Outlook topics. And I'll also say more about the projects next week. Take care. Goodbye.